Please welcome Shyam Gollakota.
All right. I'm a computer engineer at the Paul Allen School of Computer Science and Engineering at the University of Washington. 2 years back, I got interested in drones and insects. And what I'm going to do today in this talk is tell you about the progress we have made in making aerial micro-drones a reality. So why do we care about drones? Drones effectively are a mobile platform to collect vast amounts of data in a variety of different applications. A common application people talk about is precision agriculture, where you could put sensors on these drones and collect various sensing information, including temperature sensors, humidity, as well as get videos of different parts of the farm in a very convenient manner. People are also increasingly using drones in various industries, for example, for oil and natural gas exploration, by using cameras and other specialized sensors. And finally, people are using drones for disaster monitoring, where you do real-time analysis on these drones. So effectively, these drones are big data collectors and a tool for providing big data collection and analysis. What I'm going to talk about in this talk is how we are going to design insect-scale micro-drones that can, in principle, enable these big data applications. Why do we care about these insect-scale micro-drones? There are multiple reasons and multiple applications why we want to actually want these kind of drones. The first reason is that they're pretty small. And what that means is that they can start going into confined spaces. For example, you can have these micro-drone goes in between trees or plants in a farm, which you cannot really do with today's drones because they can get entangled. Or you can imagine that these things can go into pipes where you can try to figure out if there is actually going to be a leak in the pipe. The second advantage is that they're airborne, which means that they can operate in any kind of a terrain, so you can use it for a variety of different applications, including for environmental sensing in farms or for warehouses or even in homes. These are pretty small, so they're not going to be as noticeable to a human being. Finally, because of the fact that they're small, the material cost of creating these drones itself is pretty low, which means that you can start creating swarms of these drones at a really low price. So this is great. So at this point, you should be asking, I can go to Amazon and buy a couple of drones for a couple of hundreds of dollars. So why don't I just take one of these drones you buy on Amazon, shrink all the components, shrink the motor, shrink the sensors, shrink the computing, and try to get something which looks like an insect. It turns out it's actually not that easy, and the reason for it is because of the physics of what happens when you're going that small. In particular, if you think about what's happening with the mechanics, you're going to have, at this tiny scale of an insect, you're going to have viscous friction, which is going to mean that if you use things like motors, they're going to be really inefficient and probably unable to actually even get you a lift. Similarly, if you think about sensing, again, these are very tiny devices. They can't really carry a lot, which means that you can't really put huge batteries, which means that any kind of a sensor which consumes power, like GPS, is out of the question. Finally, control is another thing which is a pretty interesting case. These are very small, and when you want to control something really small, you need a fast feedback loop. And what that really means is that you need significant amount of computation on the drone itself, but again, it's a small drone, which means you can't carry a lot, which really prevents you from doing something good. So the idea that we can take something which existing designs and shrink them into the size of this insect does not really work. So what we are going to do is basically take our inspiration from the nature. So if you look at what happens with drones, sorry. All right, so if you look at insects flying, they don't really use motors at this tiny scale. What they use is wings. And you can see that these wings allow you to maneuver pretty easily. You can turn around. And they work pretty efficiently. Nature has actually figured out how to get mobility at these tiny scales. So what we are going to do is we're going to start designing drones which are going to imitate this specific behavior where we're going to use wings instead of motors. In fact, we're not the first to do these kind of drones. There has been a history of people trying to do these things. In particular, in 2005, Berkeley showed that by using piezo actuators, you can actually try to imitate the wings of a bee. But the problem is that they couldn't get any kind of a lift from the ground. So in 2007, Harvard showed that by using the same piezo actuators, by tweaking the designs, you can actually get lift. The challenge, however, is that despite more than a decade of work, if you look at what is the state of the art, you still need a cable connecting the drone to a ground base station. And this cable is being used to provide power, it's being used to provide communication to the drone, as well as it's being used to provide control to the drone. So we don't really have any kind of a wireless drone which can basically operate at this kind of a tiny scale. So last year, we got together an interdisciplinary team of mechanical engineers, electrical engineers, and computer engineers. And we basically we built a system which is the first wireless insect-scale drone to basically lift off. So we are going to put this drone, which we designed, right next to a pencil. And you're seeing that basically it has no wires connected to it, but it can effectively lift off from the ground in a very efficient manner. So it turns out, even to achieve this kind of a liftoff, you need to address a significant number of technical challenges. In particular, the piezo actuators I talked about require voltages of about 200 volts, which is really hard to get at these tiny sizes. Second, batteries are pretty heavy. If you want to basically move something, you need significant power. And if you're going to use batteries, this thing cannot really carry the huge batteries. And finally, you need to have computation and control, which again has to be done on board. So we address all these different challenges. In particular, we designed the first very tiny, very lightweight circuit, which can provide a boost conversion, which gives you these really high voltages. And to address the battery issue, we actually said, you know what, let's actually not have any batteries at all. Let's go completely battery-free, and we're going to use a solar cell to instead wirelessly deliver power to the drone itself. And because we don't have a battery, you can use that weight to carry other kind of useful sensors. And finally, we designed different approximation algorithms to show how we can actually generate this analog signal required to move the wings on a very low-power microcontroller. So these are all the different components we have in our robofly. We have a PV cell, which basically gets the power. And we have a boost converter, which takes a tiny amount of voltages and converts it into 200 volts, which is required for moving the actual wings. We have a microcontroller to basically create the control required to actually get the wings. And when you put all these things together, what we get is basically this robofly, which we could show that it could basically lift off. You can see that the robofly is right next to a bee, so you can see the size where we are at right now. So I showed you that we got a liftoff, and it turns out that we are actually on track to getting a completely wireless and battery-free sustained flight on these specific drones in the next few months. And this is really exciting, at least for me, because we are finally taking something which has been a part of science fiction and making it into a reality. So this is cool, but if you take a step back, what is the actual problem faced by drones today? The big problem faced by drones is that mechanical drones consume a lot of power. In fact, if you can buy a drone out there, it probably lasts for 20 minutes, before which you have to again recharge the battery. And the reason for this is actually pretty fundamental. If you think about what happened in computing because of Moore's law, effectively, the actual power efficiency of computing has gone up exponentially. But mechanical components don't really follow Moore's law. And as a result, they still consume a significant amount of power, and this is the reason why any kind of a mechanical drone today consumes significant amount of power. This brings us to the second part of this talk, which we call Living Internet of Things, or Living IoT, which is a flying wireless platform on live insects. So here's the idea. If we know that drones consume power, why don't we just use live insects, which can already provide the mobility, and have them carry our wireless sensors? So these live insects and the sensors can do all kinds of different operations, like sensing, tracking, communication, as well as data analytics. So here is the platform which we created. It's actually, you can see the platform on top of the bumblebee. It's a bio-based solution. We are basically using the fact the bee can fly by itself. You don't need to recharge a bee. It can feed itself. So you're basically solving one of the biggest challenges, which is the power. And it has no mechanical components because you're allowing the bee to fly by itself. And finally, from an application perspective, people already introduce these bees in farms for pollination. So effectively, what we are doing is exploiting this existing infrastructure in these farms and piggybacking our sensors on top of this to enable all kinds of different smart farming applications. So here is a video of the bee carrying our living IoT platform. This particular platform has a humidity sensor. It has microcontrollers. It has a communication capability so that you can actually communicate back the data to a base station. And you can see that the bee is, we had to enclose it to make sure that it doesn't fly away, but it's able to fly around. It's able to do its own thing without actually being it can carry the weight pretty easily. So what are the challenges in actually achieving this? There are multiple challenges. The first challenge is that we're talking about a bee. It can't really carry a lot. It's a pretty tiny insect. So it turns out that if you look at an American bumblebee, they can carry at most around 100 milligrams. So if you look at the lightest battery you can buy off the shelf, it weighs around 70 milligrams. So what that means is that all the electronics, all the smart electronics you want to design has to weigh less than 30 milligrams. And more importantly, because you have a very tiny battery, which is a 70 milligram battery, you need to be able to do all those sensing operations within the tiny amount of power you have. So the first challenge you need to actually solve is trying to get this whole thing, all the electronics and the smarts, in a very tiny weight, as well as very low power. The second challenge, which you might have guessed by now, is we cannot really control the bee motion. So if you look at a drone, you can basically control where exactly it is moving. You can basically say where you can ask it to move. But bees, people haven't actually shown so far that you can control their motion because they're really tiny insects, and it's really hard to control their motion. So how do we really get these sensing applications? So we take a slightly different approach to basically enabling this. What we do is what we call opportunistic sensing. So this is what we are going to have. We're going to have a GPS-like capability on the bee itself, so the bee can figure out exactly where it is with respect to space. So now, let's say we actually have a beehive, and we attach our platform to, say, 20 to 30 bees. They go out, and over the course of the day, they span the whole farm. At any time they are going, they're basically going to log in the temperature value or whatever sensor value you want, as well as the location at which they're actually taking that. At the end of the day, all these bees are going to come back, and we're going to create a map of the sensor data across all these bees so that we can actually get the whole sensor data. So instead of trying to control bees, we're going to leverage the fact that we have a huge number of bees in these farms and in these hives. So we can just attach the platform to all these bees, and opportunistically, when they go out there, they're going to collect the data, and hopefully we're going to get the data across the whole farm. So our solution effectively has two main solutions, two main components. First, we are going to build a low-weight hardware. The second, we need to enable 2D tracking on the bee itself. So here is a platform which we actually built. This is basically a completely programmable platform. And the way you typically build hardware is by using printed circuit boards. The green stuff you see typically when you actually see a hardware, but that apparently turns out to be significant amount of weight. So we instead build this whole hardware on very flexible and lightweight material. And that allows us to basically design the whole hardware to be less than 30 milligrams. And it's a completely general purpose platform where it's a microcontroller. So if you're a computer science person, you can completely program this. It has flexible interfaces. You can attach temperature sensors, humidity sensors, and all the different kinds of sensors to this platform. And it supports wireless communication, which is important. You want to get the data from the bee. And it has antennas, and it has all those different components. So once you get this hardware, the way you attach it to the bee is you cool down the bee for 2 minutes. That's going to make sure that the bee doesn't move as much. And then you glue the hardware to the thorax of the bee. And within a couple of minutes of actually the process, the bee is basically ready to basically start foraging for food and flying again. So that's how we actually end up building this low-weight platform, which we can attach to all these different bees. The next question, and the most important question, is how do you actually achieve 2D tracking of hundreds of these bees which are going all the way out there? So one thing you can think of is GPS. I mean, we all use GPS in outdoor environments. Farms are outdoor environments. So we can use a GPS to get the actual 2D location, and that would be good. It turns out we can't really use a GPS. And the reason for it is that GPS is pretty power consuming. Most of you would have experienced it when you turn on the GPS on your phone, it drains the battery pretty significantly. And we are talking about a phone battery. Here we are talking about a 70 milligram battery, which is almost no power at all. So if you run a GPS on it, it's probably going to last you 5 minutes. So what we did is we came up with a solution, which is a zero power positioning system, where we are going to basically get 2D location, but without consuming any power. And the way we do it is by designing a very passive receiver. When I say passive, it's zero power. All the components are completely passive in nature. And what this receiver is giving you is the amplitude of the signal. So we're going to have a base station or an access point co-located with the hive, which is going to transmit out wireless signals. And what this passive receiver is going to give you, it's going to give you the actual amplitude of this signal. So when you know the amplitude, you effectively know the range, because as you keep going farther and farther away from the base station or the router, the amplitude is going to come down. But amplitude alone does not give you 2D location, because for 2D location, you need to get the distance as well as you need to get the angle. So how do you just use amplitude to get the actual 2D location? The way we do this specific thing is we're going to use beamforming at these routers to figure out exactly where the bee is. So we're going to leverage the fact that if you think about any kind of a wireless device, even if you think about your Wi-Fi router and some of your phones, they have multiple antennas. And you can use these multiple antennas to change the phase of the signal you're transmitting. So what we do is actually very simple. We are going to basically scan the space across different angles, and when you hit the actual angle of the bee, the amplitude of the signal is going to peak. So by scanning it and looking at the amplitude corresponding to the maximum amplitude, we know exactly what the phase of the bee is corresponding to the actual access point. So by combining the angular information and the distance information, we get 2D location, which is what we actually evaluated. We deployed it in a farm. This farm is around 100 by 80 meters long. And we put the bee and the platform across different points. And what this plot is showing you is the cumulative distribution function of the 2D location across all these points. And basically what we are getting is a median accuracy of about less than 2 meters. This is cool because we are getting accuracies which are similar to what a GPS radio would give you, but without any power usage at all. And it's also pretty low weight, which means that the actual bee can carry it, and it can basically keep getting its location for the whole day and not really worry about actually running out of battery. So now that we have the location, we need to actually attach it to sensors. In fact, I showed you that we attached it to already the humidity sensor and the temperature sensor. We can also attach it to other sensors like accelerometers, so we know exactly how the bee is moving around. And we can, more importantly, attach it to a camera. And that can change the game, because once you get pictures, and these cameras are pretty small. Nowadays, you can buy cameras which weigh almost nothing, and they are really, really small. So once you get these cameras and you attach it to these bees, you can get lots of information about the farm and in different locations, which can completely transform how we do smart farming. So once you attach all these sensors, you just basically leave the bees out there. They go out there. The other bees, basically, you go and you forage on food. You can see that one of the bees actually has a platform over there attached to it. And they're going to collect the data, be it videos or be it the temperature value. At the end of the day, they're going to come back, and you're going to upload all the data. So what we're going to do next is we are basically going to do data analytics on all the data we're collecting using edge computing. We can't really do smart computing on the bee itself, so we're going to upload the data to an edge device, and we're then going to apply all kinds of different algorithms to understand what's happening in the farm. For example, you can collect the data across all the bees. You can get the video data, you can get the temperature data, you can get the humidity data, and you can collect all this location-based data and try to understand what's really happening in the farm. And this can be pretty powerful when you couple it with machine learning techniques. For example, you can try to predict what's happening with plant diseases if you actually get images where the bee is going close to the plant itself, and you can also figure out what's happening by trying to understand the trajectory of the bee itself. For example, if a bee is only focused on certain parts of the farm, you would know that something else is happening on the other parts of the farm. You can also get a pretty data-driven approach to understanding bee behavior. So now that we can put sensors and cameras on top of bees, we can actually get a bird's eye view of how the bee is seeing the world, as well as what it's actually sensing. And that will enable us to understand and answer really important questions as to why these insects are disappearing from nature. And finally, we can also use algorithms to basically combine this video data and improve the bee tracking accuracy by doing simultaneous localization and mapping algorithms. So to conclude, I talked to you about two different related things which are happening in the space of micro-robotics. And what I talked to you are things which we just did in the last 1 year. So it's very accelerated growth of what we can actually achieve in terms of these micro-drones. So what I believe, to conclude, is that we are entering the golden age of micro-drones and bio-robotics. And I think if you combine them with machine learning techniques, you can really transform multiple fields. Thank you.